Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about having buffered solutions and calculating the pH. Okay? Now, this is a buffered solution because we've got acetic acid, which is this chemical right here, and potassium acetate. Now, potassium acetate contains an alkali metal, so we know that this is going to dissolve into potassium ions and acetate ions 100%. So whatever molarity of potassium acetate I have, I'm going to have molarity of the acetate ion. And this acetate ion is the conjugate base of acetic acid. And when you have an acid-base conjugate pair, that's what makes a buffered solution. Okay. Now, this first problem, it doesn't have any of the acetate ion. It only has acid. So this first one and this last one, where something's missing, okay, they are not buffered solutions. The only buffered solutions we have here are going to be in the middle, where both the acid and the conjugate base are both present. Okay. Now this first problem then, since it's missing the acetate ion, is simply a weak acid problem because there's only weak acid present. Okay. And here at the bottom, it's going to be a weak base problem because the only thing that's present is weak base, the acetate ion. So our job today is to calculate the pH of the weak acid and the weak base problem and all the combinations where it's buffered. Okay, so the first problem, like I said, is simply a weak acid problem. So we're going to come in here and I have this equation for the weak acid, acetic acid, which is controlled by the equilibrium constant Ka, which is equal to 1.8 times 10 to the negative 5. Okay, so I'm going to go ahead and plug in 0.5 for right here, and the acetate ion, there's nothing present. Okay, so this is going to be 0.50 minus x, which we're going to approximate as 0.50 because we think this x is going to be small. This is going to be x, and this is going to be x. So this is going to end up looking something like this, where it is the products, x and x, over the reactants of 0.50. So I'm just going to bring in my calculator in here, and I'm going to do some calculations. I'm going to do some cross multiplication. 1.8 times 10 to the negative 5 times 0.5 is equal to x squared. So I'm going to take the square root of that answer in order to find out that x is 0.003. Now remember, x is going to be equal to hydronium ions. So if I want to figure out the pH, I got to take the negative log of the hydronium ions, which is equal to 0.003. So negative log of that answer is going to give me a pH that's equal to 2.52. And I'm going to put that in as my answer. So it's just a simple weak acid problem. Okay, great. Okay, well, what if it was buffered? What if there was both acid and conjugate base present at the same time? How would that look different? Okay, not very different at all. Okay, the only difference is I would plug in my acetic acid for right here, and then for the acetate ion, I would come over here and put 0.10, and then just fill out the chart. 0.40 minus x is 0.40 minus x. Of course, we're going to approximate that. This is always going to be the same, 0.10 plus x, which we're going to approximate as 0.10. And then we're going to plug in the products, x times 0.10 over the reactants, 0.40. And we're going to bring in the calculator again to do this problem. Okay, so 1.8 times 10 to the negative 5 times 0.4 divided by 0.1. It's going to give me an x value that's equal to 7.2 times 10 to the negative 5. And if I take the negative log of that, I will get the pH, which is going to come out to be 4.14. So come up here and go ahead and place 4.14 as the answer. And this process just keeps repeating itself, okay? I'm going to do two more just so that you get a handle of this, okay? So this is going to be 0.3, and this is going to be 0.2, and it's products over the reactants, and then it's plug and chug. So 1.8 times 0.3 divided by 0.2 gives me an x of 2.7 times 10 to the negative 5, negative log that to get the pH, or we're around that to 4.57. Okay, now you might say, well, I think I got the hang of this, okay? But I wanted to go one more time because there's something special with the next problem, okay? And that is the acid and the conjugate base have the same exact concentration. And there's something special with that one. So I'm going to come over here and star it. And as you can see, if I fill out my chart, I'll get something like this. And if both of these are exactly the same, okay, well, what's special is that they will cancel each other out. And x is simply just equal to the Ka value of 1.8 times 10 to the negative 5. Now I can just come in here and do negative log of 1.8 times 10 to the negative 5 and get the pH of 4.74. And then I'm going to go ahead and fill that into my chart. But I want to talk about why that is special. Okay, so when these are exactly the same value, you can see them canceling out. But remember, x is equal to the hydronium ions, and that's going to be equal to the Ka value. And if we take the negative log on both sides, well, the negative log of hydronium ions is simply pH. And if we take the negative log of the equilibrium constant, we're going to call that pKa. So you get this equation that pH is equal to pKa, and the only time that happens is when these concentrations are exactly the same. So that answers this question down here at the bottom. What is so special about having equal molar of acetic acid and potassium acetate? And when they're equal to each other, pH is equal to pKa. Now, if I continue this process of just plugging in the acid and the conjugate base, you're going to get pHs of 4.92 for the next problem and 5.35 for the problem after that. But the one that I really want to talk about is that weak base problem. So I kind of want to work that problem out with you. Okay, so I'm going to come in here and grab a piece of paper. Okay, and we have nothing but weak base for this particular problem. Okay, and when you have nothing but weak base, you have to write a weak base equation. So that's kind of like where it starts. So the only thing that's present is the C2 H3O2, the acetate ions, and we're going to put that with water. And what bases do is they accept protons. The proton's going to go in this direction. And if the proton goes in this direction, what's left over is a hydroxide. Okay. Now, if this is a base equation, we're going to need a base equilibrium constant. Okay. When we fill out our ice chart, okay, 0.50 goes under the acetate ion because we got a base equation. And we don't have any of this, so this is going to go down x, this is going to go up x, 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 and this is going to be 0.50 minus x, which is approximately 0.50, okay? And Kb is going to equal to the products, x times x, all over the reactants, 0.50, but what we need is we need that Kb value. And I want to remind you, in order to find a Kb value, you use the Ka value because Ka times Kb equals Kw. And we know that Ka was equal to 1.8 times 10 to the negative 5 times Kb, and that's equal to Kw 1.0 times 10 to the negative 14. So we're going to divide both sides by 1.8 times 10 to the negative 5. And that will give me a Kb value. Okay, so I'm going to come in here with my calculator. 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5 tells me that my KB is equal to 5.56 times 10 to the negative 10. So I'm going to come in here, 5.56 times 10 to the negative 10, and I'm going to do my cross multiplication. So 5.56 times 10 to the negative 10 times 0.5, that gives me x squared. I want to take the square root of that answer. Okay, so x is going to be equal to 1.67 times 10 to the negative 5. Now remember that x is hydroxide, so if I take the negative log of that answer, that's going to give me POH. So the negative log of the concentration of hydroxide ions is POH as 4.78. Of course, if I want a pH, I'm going to 14 minus that answer. And I get a pH of 9.22 as my final answer as far as the pHs are concerned. If you found this content helpful, okay, please give it a like and subscribe. Just want to remind you again that the first problem is just a weak acid because it's just weak acid. The last problem is just weak base because there's only weak base. And then all the problems in the middle have both the acid and the base, and that's what makes a buffered solution. And if you found this content helpful, give it a like and subscribe. When you add a comment, it really does push this information out to other students that are interested in learning chemistry.